Good afternoon and welcome to our interview with Dr. Cynthia Sisson. She comes to CSU from Louisiana State University in Shreveport, and she will be telling us a little bit more now about the seminar that she just gave for the faculty here on Dino software and the tablet PCs that she titled Trading Lecture for Learning. It's an intriguing title, so we'll follow up and learn more details about it. Before we start, maybe a few words about Dr. Sisson. She got her Bachelor of Science in Physics from New Mexico Tech, and she got her PhD in Computational Physics from University of South Carolina. She was primarily dealing with simulations of high-temperature superconductors at that time, but more recently she's been working on simulations of light propagation through human tissue. She is the first endowed Elmer Simon Distinguished Teaching Professor at LSUS, and for the last maybe 10 years or so, right? She's been involved with the science education in a variety of different ways, and in particular through the first NSF FIRST program. That's the acronym that stands for Faculty Institutes for Reforming Science Teaching. And this is an NSF program that she's been involved for past 5 years or so, right?
5, 7, yeah.
Right. Now, with that, I would like to turn over and ask Dr. Sisson to tell us a little bit more about this technology that she presented today about and how she uses it in her introductory physics classes.
Well, sure. So the first question is, what is a tablet computer? And the first thing that you need to understand with a tablet computer is that it's a computer that you can actually write on as a tablet. So I wanted my students to be able to solve physics problems in a way in which that they, in the same way that they would be solving problems on paper. So students actually write on their tablets, and here, you know, I'm actually writing on a thermal energy problem, but we're solving problems as in the same way in which that we would be solving problems on paper. So we can draw diagrams, we can write out equations, we can do everything that we do on paper, but we have the speed of technology for communication so that we can actually, I as the professor can see what my students are doing very quickly.
So how would this look like if you did not have a tablet PC?
This would be a wall of chalkboards or whiteboards with me walking around trying to figure out what the students were doing, or it would be a bunch of transparencies. Actually, I've tried that in the classroom, and you get transparency, you get ink all over your fingers when you try to go through and see what the students have done. It would be much slower. I had tried it without technology, and I was frustrated by it because it was too slow. I needed something that was faster and something that let me look at student work, find the really good examples, and then put those examples up on a projector and show my students, this is what I like, this is why I like it. Or even better, put it up on the projector and have my students explain, this is what's good. And I can do that without letting them see the bad examples, which is what you get if you put it on the whiteboard or the chalkboard.
So basically you're saying you're presenting their own examples as they solved them on their tablets.
I am presenting student work to students, exactly. But I'm only presenting the good work.
All right. Now, there seem to be two parts to the whole process, right? One is tablet PC, and you just told us what hardware looks like. But another part is this software. Can you tell us more about how they interplay and what? Absolutely.
The software was very important. The first semester that I tried to do this, I wound up using some software that didn't do the job. It kept crashing on me. And so we used a shared network drive. Students would upload their work to the network drive. I would then open up 20 different files and look over their work and pick out the one or two that I wanted to present. So I could still do most of what I wanted to do there, but it was slow. I was still losing time to just looking through different files. With Dino, which is what I'm using now, with Dino, it's great because I can very quickly flip through student submissions. I don't have to wait for them to upload it. I can actually look and see what they're doing at any time, and as they're doing it, I can actually interrupt them if they are all heading off in the wrong direction. I can just stop and say, whoa, 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 stop. You need to be thinking about this instead of that. I can catch them as they're making mistakes, correct those mistakes, and get everybody going the right direction. It's been wonderful to have a software that actually lets me do that. And it has all the other bells and whistles as well. It can do student polling. Mm-hmm. You can ask questions of students. You can have different groups of students on different tablets collaborating together on the same problem. Mm-hmm. Lots of fun things to do.
Okay, so basically, let me pull back just a step and try to make sure that we see the big picture with the technology that you're using. So all of your students, or one or two of your students, are sharing one tablet PC. Yes. You have your tablet PC, and now as you write physics problems and doing your lecture, you're not anymore doing that on the chalkboard or on the whiteboard. You're doing that annotating on tablet PC. Now, as you do that, what does the software do as you write?
So if I'm using the software in the in lecture mode, where I'm actually talking and working through problems, as I write on my tablet computer, what my students see is that writing showing up on their tablet computer. So they actually are immediately fed my work. They don't have to be going through the process of taking what they see up on the screen and transcribing it to their notes. It's already there in their notes.
So do you see a problem with them possibly phasing out and just letting you do the work and not participating? And because
I don't let them do that because I'm not using this technology to do a traditional lecture. I'm not using the technology to stand there and give a lecture in which I'm writing down information and my students are copying it. Instead, I'm using it so that I might write a little bit, I might get them started on a problem, but then immediately it pushes off and onto their shoulders, and they have to do the next step.
So basically what you were telling us is the situation when they write on their tablets and solve the problems that you assign to them. Do they do this individually, in groups?
They do this in groups. I was originally concerned about the fact that I had more students than I had tablet computers, but it turned out to be a wonderful serendipitous problem to have, because that forced my students to work together. It forced them to work around a single tablet computer, and they worked cooperatively so much better because there was this piece of technology sitting between them that they had to share to solve the problems. I had been trying to get students to work in groups for 3, 4, 5 semesters prior to this, working through problems, and I had, these are science majors, and some of them take themselves very seriously, and I had in some classes a whole set of students who would just kind of cross their arms and not talk to each other, or say, B, yeah, I think the answer is B, and that's it. That's as much as they would get in terms of collaborating. Put them in front of a tablet computer and say, solve this problem, work it out, have things that they can write on, and know that their work is going to be shown up on the screen, and suddenly they're talking and they're interacting, and they're sometimes stealing the computer from each other and saying, no, I think that's wrong. It becomes much more collaborative. It really forces that collaboration.
Now, you mentioned that it's now easier for you to figure out what they're doing.
Yes.
So are you going around the classroom and just looking into their tablet PCs as they do that, or is there?
The software does that for me, so I can pull up, I can either ask them to submit what they have done when they're done with it, and that means that I know that I'm seeing what they think is the final answer, that they think that they are completely done with this problem. Or the other way that I can do it is I can basically peer over their shoulder as they're solving it in a technological sense, which is that Dino allows me to actually download their work as they're doing it and see, are you on track? Are you working towards the end goal? What kind of progress are you making? That also lets me time my classes a little bit better, because now I don't have to ask, okay, are you done? Are you getting close to being done? And they don't have time to go off and do things like, play solitaire and stuff like that.
Right. So basically, you're seeing all of this from your computer as
Yes.
they submit. What do they say? How much do they like it? How much did it take for them to get used to it?
I spend one day at the start of the semester, just introducing them to the software, doing some very simple problems, and then also taking them through all of the different things that they will have to use throughout the semester, and and giving up that first day to get them acquainted with the software just pays dividends throughout the semester, because then they know how to use it and they can use it smoothly, seamlessly for the rest of the semester. So I do definitely recommend get them used to it in the first recitation. The first day you use it, they'll be fine with it from then on out.
The software appears pretty user-friendly in this respect, right? It doesn't take long before they're up to it.
Right. It's a technological generation, and it's pretty much what you expect. So they can figure it out quickly.
Right. Now, you were telling us just earlier about the results, meaning as neat as it seems, after all, we want them to learn better.
Right.
And the question is whether or not it makes sense to spend all of this money on hardware and software. So can you tell us more about what did you find?
Sure. So it's not just a toy. It's not just something to make them say gee whiz and hope that and hope that they enjoy the class more. They enjoy the recitations, they like it, but also they are learning. They are more successful. So I've seen an increase in problem-solving skills in my classes because of this, and I have seen an increase in success rates, which surprised me a lot. Success rates being the number of students getting A's, B's, and C's compared to the number of students getting D's, F's, and W's. In one class I went from, historically in introductory physics, we had a baseline of somewhat less than 60% of our students getting A's, B's, and C's in that class, and some semesters it was down as far as 40% or sub 40%.
Right.
And in the class where I implemented this first, the number of students who got A's, B's, and C's jumped up to almost 80%. So it almost doubled from the lowest that I had seen, and it went up by 2 standard deviations from what the baseline average was for that class.
In terms of their retention, how about their scores?
In terms of their scores, I used a paired final exam, so I used a final exam from a final year. And in my university physics and my calculus-based physics class, they went up by a significant amount. They went up by 11% on the final exam. I think the first time I gave that final without the tablets, the class average was 57%, which is not a class average that I like to see. And it went up into the very high 60s when they took it after having had a semester in which we worked on problems using Dino and tablet computers.
Right. So you're basically saying you were able to increase the number of students that succeed in the course, that do not drop off, and within this larger pool, you had higher success rate in terms of the success in their final exam, right?
That's right, and that was the part that surprised me. I was hoping to see better problem-solving skills, but what I didn't really understand was that I was also keeping more students to get all the way to the final exam.
Right, right.
So I'm actually keeping more students. Fewer students are dropping, fewer students are switching to audit. And they are, when they get to the final exam, they're performing at the same level or at a better level than my previous classes. So I've got the same standards, but my students are now rising to meet those standards. It's been very fun to see that this is a way in which I can help my students, get up to that level that I expect.
Right. You were showing us earlier features of the software, and you showed some transfer of slide. When you clicked on the slide, it appeared on our screens. When you annotated, that annotation was showing up. You also showed we can chat back to you.
Right.
You can we can list multiple choice question, and we can give you the feedback, and you have immediate results. We can submit the slides and so on. All of these features. Would there be one that you would pick up as your favorite?
Oh, I couldn't do this without the ability to grab student work and pull it onto my computer and look at it immediately. The polling feature I like, but I can do that with clickers, and I do that with clickers on the days when I'm not using tablet computers. But the fact that my students can write and draw They can use equations, they can draw pictures, they can draw, this is physics, so force body diagrams. They have all of that, and I can look at it and see it immediately. That is the most important, that's the most important feature for me. It might not be for other people, but it's, physics is such a visual field that's what I need, and that's why I use this.
Right. Do you see this equally valuable or applicable in other fields? Maybe math and engineering as maybe similar fields, but maybe also other fields like psychology, sociology, geography, history.
Certainly throughout the sciences, I can see that it would be valuable. I've taught a few introductory computer science classes because I'm a computational physicist, and this would have been really useful in those intro programming classes. It would not have to be so visual there. We wouldn't need the pictures and the drawing and the equations, but you could immediately see that having students, type in a code fragment that does the following thing. You can pull it up. And actually you could split a screen and have two groups doing it simultaneously, and they can see, are we solving this problem the same way as another group is? Because sometimes you've got multiple ways of getting to the same right answer. Right. Computer science, I think, would be great. Math, it's fabulous. Again, you've got something that works like a piece of paper, but you can also go in and see what the students are doing and show right answers and stuff like that. Chemistry, some chemists at my university have been using it. Mm-hmm. Biology, our genetics professor has been using it in her class. All of those, very useful. I don't know well enough how I would apply it in other areas, but I really think that it would be very useful, especially for the collaborative elements in it. You can get students working collaboratively either around a single tablet or even between different tablets. You can actually group people randomly, or you can group them in ways that you want within the software, mm-hmm. and say, come up with a solution to this particular problem. Right. So you don't have to be sitting right next to each other to
right.
solve the problem.
Right.
You can actually have people on opposite sides of the room working on the same problem, working on it together. It also means they get to know more people in their class than they would. They don't just know the little geographic area around them, they know everybody.
Right. So could we conclude with your suggestion for other university professors? What would be your take on how they might benefit from this technology?
Well, I think that it's our responsibility as university professors to try to help our students succeed. We know what we want our students to know and learn. We know what we want. We know how we want our students to demonstrate that knowledge, but we need to figure out the ways in which we can get them there. And I think that using as many different interactive, collaborative ways as we can to get our students there is one way. I think that using software like this, having engaged classrooms, something more than just a professor at the front of the room lecturing, all of those are ways in which we can help our students succeed.
Right. And would this be applicable for different educational levels as well as different fields?
Oh, sure. It's used everywhere from elementary schools up through upper level classes and graduate classes. So I think it's appropriate.
I want to thank you very much. It's been a pleasure to have you during the interview. It's been a pleasure listening to your seminar just earlier. I invite you all to join us and see the seminar that will follow this interview. And with that, I want to thank you for being with CSU and hope to have you soon again here.
I really appreciate the invitation, and thanks so much.
Click on submit balance or play with it, whatever. It shouldn't be too bad, and if you're lost, you just give up.
It would be really nice if somebody would be willing to sit at one or two of the computers so that we can see what it looks like.
Because that way we will see more than one more than one answer choice submitted.
I'll jump on that one.
Yeah, during the demo part, so you can just jump on it and good deal. So they said they're going to broadcast this live, but I'm not sure if we're on or not. Michael, shall we pretend we are? Thank you very much all for coming in. I'm extremely pleased to introduce Dr. Cynthia Sisson today with us, who teaches at Louisiana State University in Shreveport. She's Department of Chemistry and Physics. She told me it's the alphabetical order, just so you know.
Has nothing to do with priorities.
She got her BS in physics with minor in computer science from New Mexico Tech. And after that, PhD in computational physics, and her area of research while in PhD program at University of South Carolina was simulations of high-temperature superconductors. More recently, she's been involved in simulations of light propagation in human tissue. She's the first endowed Elmer Simon Distinguished Teaching Professor at LCUS, and for almost a decade she's been involved with science education, and in particular with NSF-sponsored FIRST program. That stands for Faculty Institutes for Reforming Science Teaching. She's now heading to the University of Georgia Marine Institute on Sapelo Island. She'll be giving a workshop about FIRST project for biology postdocs, getting them updated. So we're very pleased to have her with us on her way to Sapelo Island. With that, I would let you take off, and you all, everybody else, enjoy yourself.
That's it. Well, thank you very much. Let's see if we can get this to cooperate. Yay, forward. Okay. Actually, back might be good.
We will turn the lights off only during the demo part. So.
Yeah, we can leave it up until we want to do a demo. So I want to thank Z for allowing me to stop off here. I was planning on driving from Shreveport to Sapelo Island, which is about a 15-hour drive. And there's something in me that says that you're just supposed to do that in one day. But this gives me the excuse to actually put it over a couple days' drive. And I guess let me give you a little bit of background about the university I come from to put this whole talk in context. LSU Shreveport, LSUS, is one of the members of the LSU system. We're a school of about 4,500 students. We have a large science enrollment because one of Louisiana's 2 med schools is in town. So we've got a lot of pre-meds, and then we've got a fairly big science enrollment overall. But it is 4,500 students. We do not have a master's program, and in particular, we don't have a master's program in physics, and that is really a lot of what drives what I'm doing here today. I'm in a program without graduate students, without teaching assistants. A lot of the things that I think of as luxuries that you get at the big universities, which is graduate students teaching labs for you, graduate students teaching recitation sections for you, doing grading, stuff like that, doesn't exist at LSUS. If I want something to happen, it has to be done by the faculty, and it has to be done within the context of our current teaching assignments. So that's where I'm coming from, and that's why I wound up trading lecture time, actually giving up one of those precious days of lecture every single week to turn it over to the students. That's why I thought this was important enough to do in lecture time, and so yeah. Let me move on and tell you what I did and why I did it.
Cynthia, your microphone is covered. You might want to.
Here. Okay. So let's go forward. So this breaks down into pretty much thirds. I want to give you some idea of motivation, why I thought it was important enough to do this that I actually willingly gave up 1 out of 3 days a week to my students. I'll talk about some of the science education research that backs up why I thought it might work. And then we'll move into a demo, how I implemented it, what it looks like. We've got 3 computers here that are all hooked up as students. You can kind of see how Dino works and what it looks like in a classroom, some of the capabilities that it has. And then finally, I'll show you results that I have from 2 years of lecture or 2 years of implementing it. I've been doing it again this spring, but I don't quite have that data yet. So I'll talk about the 2 years that I have the data on that has been very encouraging. So let me get a sense of what sorts of faculty we have here. What areas are you in? I guess
physics and astronomy.
Physics, okay.
Physical education.
Physical education.
Computer science.
Computer science.
Health science.
Health science.
Physics.
Physics.
Math.
Math.
Physics.
Okay, I'm going to admit, being at a small school, sometimes you're a jack of all trades. Computational physicist, so I've taught the introductory programming classes a few times when they were shorthanded. So I know some of the pain that you have in computer science, and there are definitely some ways that you could apply this. I was hired at the expense of a math position, so I've taught calculus a couple times in that first year and a half or so until they managed to hire in another mathematician. So again, there are definitely some applications here. Definitely applications that span certainly much farther than physics, certainly even beyond the sciences. I'm a scientist, and I think of this in terms of scientific teaching, so that's where my focus is going to be. But please do, every time I say physics, just think science or whatever your field is. Okay. So for about the last 10 years, I've been involved with education research. And one of the most important things that I have come out of it with is that we're willing to teach anecdotally. We're willing to teach just the way that we've seen people teaching, or the way that we've always been teaching. And yet we do our science much more carefully and much more rigorously. And so what scientific teaching really wants to do is say, we need to approach science in the same way that we approach our research. And that is to ask good questions, to make measurements, to get data, and have that data drive what we do in the future. So data needs to tell us what the best way, needs to tell us how we should move forward. And right now that seems to be saying that we want to engage students. If you just stand up in front of a class like I am right now and lecture at them, they get very little out of it. Having them doing things, thinking, talking to each other, that's what the research seems to say is a better approach. So, oh boy, okay. Let's put all of these up here at once. These are the 3 questions that I think we really need to be asking. Certainly whenever you teach a new class, and whenever you are thinking about redesigning a class. Preferably every single semester that you teach, but we don't always have that luxury. So approaching it as science, what do we want our students to know and do? What skills should they have coming out of this class? And then what am I going to accept as proof that they can actually do it? So what assessments am I going to be making? If you say, I want my students to be able to learn to think critically, well, how are you going to measure that with a multiple choice test? It has to be a very well-designed multiple choice test if you're going to do that. You have to think really hard about how what you measure aligns with what you say is important. And then, of course, the design part is how do we help our students get there? What do we do to make sure that our students can actually show us evidence that they know how to do what we want them to know how to do? And Diane Ebert-May, who I attribute that to, is she's an ecologist, and she is also a biology education person. She has been the driving force behind the first projects, Faculty Institutes for Reforming Science Teaching. I got involved with first when it was first 2, we're all the way up to first 4 now. These days we're focusing on postdocs because they're nice and malleable. If you teach them the fundamentals of what research says is good approaches to teaching, they seem to be able to go forward and apply it. Okay, so the question that I was asking was the important thing. Actually, I should go back here. Let me see if I can get this to work. What do we want our students to know and be able to learn? Or be able to do one of the things, not all of the things, but one of the things I wanted my physics students to be able to do is solve complex physics problems. And I can break that down into saying they need to be able to solve a complex physics problem by breaking it into much simpler solvable pieces. They need to be able to identify variables, draw a picture, all of the things that you who are physicists or who have been through physics have had to deal with. So I want them to be able to do that. That's a skill they need to come out of the class with. What's the evidence? Well, I'm talking about solving physics problems. The evidence is pretty much final exam, which is problem solving. And here's the part where I realized, oh dear, I've been spending a lot of time on getting my students to think conceptually about physics. We're doing pure instruction, we're talking about concepts of physics, we're really hitting that hard, we're modeling a lot of that, we're helping them construct that understanding in the physics classroom. What am I doing for problem solving? I solve a problem and then toss them into the pool of homework and say, okay, solve these problems yourself. Go home, go away where you have very little in terms of resources and somebody looking over your shoulder and saying, this is how you do it, and figure out how to do it based on having seen me do it once, maybe twice in class. So, oh, that bothers me. I'm not really helping my students get there. So I wanted to give my students more tools in terms of learning how to solve problems. I wanted to actually teach them some of the methods of solving problems. And let's go forward from there. Oh, recitations. So recitations, certainly in a physics setting, just means problem-solving session. So what I wanted was a recitation, and that's certainly when I looked enviously at the big Research One universities and all of their graduate students and thought, oh, I wish I could just add a recitation section or add multiple recitation sections to these classes, have graduate students teach my students how to solve problems. Then the world would be perfect. But no graduate students. And the administration was perfectly happy to let me add a recitation section to our physics classes, as long as I taught it with no extra teaching load. Certainly my faculty were not about to volunteer for that, and I wasn't all that thrilled about that myself. I thought, okay, can I do this in the context of the existing class? And so now let me talk about some of why I thought this was so important. Let me talk about some of the science research behind it. So I've been doing this anecdotally so far. Let me bring it back to the data. This is one of what I think of as sort of a foundation paper in science education research or in physics education research. Hake, 6,000 student survey of physics students, in which we give students a conceptual pretest in which we tell the students we're just trying to get sort of a feel for, it's a diagnostic test, we're trying to get a feel for your background knowledge in this material. Don't worry about it, you're not supposed to know everything, but it is conceptual, so they don't have to do any problem solving. They just take the test. For physicists, this is force concept inventory. And then at the end of the semester, you ask them to take the test again. They don't know it's the same test. They're not told it's the same test. And you compare post-test to pre-test, and since everybody starts out at a different place, you divide that, you normalize that by the gain that they could have gotten. So 100% minus the pretest. How much did they learn of what they could have learned? 0 is going to be they came in knowing something, they left knowing exactly the same thing. They didn't gain anything. A gain of 1 would be they learned everything possible. I don't know anybody who has ever gotten a gain of 1. I would like to meet them and meet their students. That would be fabulous. You can see numbers here range from 0.08 up to 0.72. Basically, he binned the 6,000 students and all of these different classes from around the country, high schools, I think some community colleges, definitely some bachelor's level, master's level institutions, all the way up to R1, and asked professors, how do you teach the class? Is it traditional lecture at the board, or is there any kind of interactive element? Do you do peer teaching? Do you have students working in groups through tutorials? Do you do any modeling of physics? What's going on in there? And so that brings me to what this means. The classes that self-identified as traditional courses are way down here at the low gain, right? And there is definitely a much bigger spread in the interactive engagement. Anything other than traditional lecture is basically what that is. But it's also pretty reliably higher, than the traditional. So this is straight lecture. And this is any kind of engagement. And that says your students are much more likely to change how they think and learn things if you get them thinking and doing things in class. So, got that? So that was a conceptual drive towards engagement. And then I saw this paper that came out a couple years ago in which a group compared. This was one of those wonderful R1 schools. They've got all these different recitation sections. And so they compared types of recitation. So students in cooperative learning groups with instructor checkpoints, that was one method, to traditional, I think of that as monkey at the board kind of recitation. The student says, can you please show me how to do problem number 5? And the graduate student goes up to the board and solves problem number 5. Traditional. But also working through a tutorial as an individual, working through a tutorial in a group, and working through a tutorial in a group but with some checkpoints in it. In physics, because there are some ways in which you can go conceptually very wrong, it turns out that if you put students working in a cooperative group but you don't give them any sort of overseer to make sure that they're going the right direction, they can head off they can head off very far in the wrong direction. So that actually wound up being pretty bad. Working through a tutorial, traditional, did not work very well either. And what worked best was, let's have people work in groups. Let's work through problems, but let's have some checking in. Let's actually see what's working and what's not and make sure that everybody's going the right direction. So I thought that sounds promising. I like that. That's what I want. A whole lot of words on this slide. I mainly wanted to say it's not just physics education research. There is research in other areas. It's just the physics ed research that I know best. Basically, every area where we have measured the data, it seems like working in a group helps students learn. Collaborative group learning enhances critical thinking. One thing it does is it provides immediate feedback, so they know immediately, am I right or not? Instead of do the homework, turn it in, think that you know how to solve the problems, and then a week later get it back and realize, oh, I didn't know how to do that at all. I was completely off base. So it catches them as they're constructing that knowledge and forces them into correct ways of thinking. Okay, so let's get past that. How many of you have seen this in your office, in your classrooms? Anybody had a student come up to them and say, I don't know why I'm having such trouble with this on tests. It looks so easy when you do it. I understand perfectly, and they think that the solution to it is that you just need to show them more problems. You need to do more examples in class. I think as humans, we have an innate understanding that if something is physical, we need to do it ourselves. Nobody thinks that if you watch golf on TV, that you're going to get better at golf. Right? Nobody thinks that watching somebody else run a marathon is going to make themselves more fit. But we also have this really deep-seated belief in our ability to mimic. So mental skills, we think, I watched somebody else do it. I should be able to do it. It looks so easy. I understand perfectly what they're doing. And students don't quite make that jump. Students have a hard time with that jump. So that was my motivation. I wanted to actually force them to to work on their problem-solving skills, to get past that golf on TV mentality, and into that you actually have to practice this yourself. You're not going to learn it until you do it yourself. Shorten the feedback loop so that I could catch them as they made those mistakes that I knew they were going to be making. In my class, I don't know if other people have this problem, I tend to give tests that are too long. And they seem perfectly reasonable to me because I sit down and I look at the problem and I know how to solve it. Whereas with my students, they look at it and they think and they wonder and they erase. I wanted to get them into a practice of, I wanted to get them to be able to solve problems more quickly. So I wanted them to have more practice with really pushing. They go home and they think that I can solve problems if I just throw enough time at it. I certainly have had some pre-meds especially who think that the solution to every problem is time. If I'm having trouble with this class, I just throw hours and hours and hours at it, and I can do it perfectly. And they tell me, if you just gave me a take-home test, I could get 100%. And I know that. But they don't get to do that on my tests. They don't get to do that when they take the MCAT. And they don't get to do that when they are actually in medical school, and they have far too much information to digest, far too little time to digest it. So they really need to learn how to speed up. And personally, I thought that I had gone a little bit too far towards the conceptual side of physics, and I wanted to come back to sort of my home of problem solving. And let's go through this real quickly. This is the problem of being in a small institution, right? 4 physics faculty, no teaching assistants. I didn't have any adjuncts who were volunteering to teach recitations for really poor pay multiple times a week. It's just they weren't coming out of the woodwork. And our teaching schedules were already full. So I needed a way to add recitations without increasing the time demand. And that's what brought me to Dino. Let's see. Yeah. And this is my workaround. Okay, so I took my lecture days, and this was really hard for me to do. In some areas, there's flexibility to what you teach in that first semester or first year sequence. In physics, we don't have that, right? You are expected to teach this much in first semester and this much in second semester, and this is the content, and you have to cover it. And giving up a third of all those days was just, it ripped my heart out. It was, how can I cover that material? But you can do it. You put a lot more off on the students. You ask them to do a lot outside of class. You ask them to do reading outside of class. And you just keep moving. So I decided I would try it. I thought it was important enough that I would try giving up one of those days a week to a problem-solving session so that they could have that recitation in spite of the fact that we didn't have the resources to give them sort of a real recitation. Here I'm being a little bit vague. A variety of methods were used to exchange information between student, tablet computers, and professor. What that really means is that the first time I tried doing this, I tried doing it with some free software, which crashed as soon as we got about like 12 or 13 tablets on it, and I was trying to use 20. Get up to 12 or 13, it would crash. 12 or 13, it would crash. By week 2, I had decided this isn't going to work. And so then we moved to what was basically a kludge. We had a shared network drive. Students would push their recitation documents, which were in Windows Journal format, onto the shared tablet drive. As they were solving the next problem, I would go through those Windows Journal documents, and then I would project the good ones. This was frustrating for them and frustrating for me. By the second time I taught it, I moved to Dino, and it has been so much nicer. Dino is just a much cleaner, simpler, more powerful way to do this. I'm not going to back away from Dino anytime soon. And then that whole checkpoint thing, I interrupt them from time to time. I give them a problem, they work on it, and then we interrupt and I say, okay, here, I really like the way this group did it. Or they'll have 2 problems side by side that are related to each other. and I'll have even tablets work on one problem, odd tablets work on another problem. I'll say, okay, talk to the group next to you. Explain what you did. How does it relate to how they solved their problem? We get a lot of interaction about how problems are solved. They get to see not just how they solve problems, but also how other people solve problems. And I will walk through some of what I consider the exemplars and say, this is what I really like about this group. Or I'll find an exemplar and I'll ask those students to explain what they did and why they did that. So there are lots of opportunities for really getting them to think and process and talk about what they're doing. And I don't shy away from it as long as I've got them there. I also show them some of the bad examples. I try to be very careful about this and only pull in anonymous bad examples, but I will pull in some bad examples and say, okay, what went wrong here? There's a problem. Find it. Find it and then don't do it on the final exam. Or find it and don't do it on the test. Don't do it on your homework. Be careful of this. My students, I asked them to tell me what was most valuable. Certainly seeing the good examples were most valuable, but they were also helped by the bad examples as well. Okay. And then some of the advantages. Why did I want to use this over, say, low-tech? We could have gone low-tech with this. I've seen people use transparencies. I've seen people use whiteboards. Whiteboards actually are okay, especially if they're small enough that you can kind of carry them around. But tablet computers mean that my students can actually write on the computer as if it's a piece of paper, and you can't really tell here. Yeah, we're going to have to unlock it, but at least I can show them. My students are doing this on their tablet computer, so it writes like a piece of paper, and it is also important to. So it's important to me that they can draw. They can draw pictures, they can write out equations, and it works just like it's going to work on a test. I don't want any keyboard stuff. I don't want any having to figure out drawing menus and stuff like that. That is not helpful at all. I wanted it to be as close to the process of test taking as possible. But I also wanted to be able to see their work really quickly. If you've ever tried doing this on chalkboards or whiteboards, you kind of have a choice. You can either have them working on different problems, and then you go around and try to have them explain, but there are going to be wrong answers up there if you do that. And that, I hate letting my students see wrong answers unless it's for a very specific purpose of saying something's wrong here. And I don't want it to be identified by group or by student or anything. So I didn't like that. You can put them all on the same problem on whiteboards, but then there's a lot of kind of looking over and doing what the group next to you is doing, and it's still slow. You kind of have to walk around and find the good ones. Here I can pull up all of their answers and just kind of flip through them computationally, find the good ones, pull up that good one and say, okay, interrupt them, and say, let's look at this one because I really like it.
When you have them working in groups on the tablet PCs, how much of the listening in on the group next door do you get?
Not as much, it seems like, as when they're up at the whiteboard, where it really seems like they just freak out about the fact that they're out of their safe space. On tablet PCs, they can be sitting at their chair, they're at their desk, they're all kind of turned towards each other. Yeah. Whereas when they're at a whiteboard, they're all kind of facing the whiteboard. What are they doing? They're like this, going, do you know what to do? I don't know what to do. What are they doing? This seems to just sort of pull them together. And actually, I don't mind if they're stuck and they rotate to another group and say, what are you doing? That's good, because that is giving us that collaborative stuff. That's still getting some of that group dynamic stuff going on. Okay, so yeah, this is sort of what it looks like. You can see the physics book and the computers, and they're writing out equations and stuff. I did break down my second year, and I also hired an undergraduate physics student. One of the problems with technology is just that you have to get it started. That takes time. You have to put it away. That takes time. And I realized that it was worth my time, and it lowered my student frustration level if we had a TA there who just pulled the computers out before class and got them turned on, so they didn't have to wait for the boot cycle, and who could just accept computers at the end of the day, shove it into the cart, and the students wouldn't have to worry about turning off the computer, waiting for it to log off, anything like that. So that has been really useful, and it means that I get to employ a physics major as well. So it's always good to have a few student worker jobs around for your majors. And yeah, now let's see if we can go into the demo. Let me
if you would,
unlock
what is your group
these.
structure? Do you rotate people in groups? Do you have assigned groups? How do you kind of interchange? Or
I have done permanent groups, and I've done that after a few semesters of teaching, a few years of teaching science education classes where I tried moving students out of a group, rotating students through different groups, and I found out how much students hate being taken away from their group. Even if it's a group of strangers, by the third week, they're saying, "You can't move me to another group. This is my group. This is my group." Okay, so I let them. Oh yeah. Okay. So right now we can see Z, who is a student, and this is my slide. This is the sort of thing that my students would see. I just pulled in a recitation from February of this year. This is going to be. Oh no, it's not. I have this. So one thing that happens is that. Well, okay, we erase. Let's try this again.
Try to pick your pen up there.
Yeah, pen. Okay. Please put group name.
Notice what she's writing there is showing on my screen.
And submit. Usually the first thing that I do is ask them to put their group name on the front slide, so I've got a list of basically its attendance, who's here. As I write here, whatever I do shows up on all of the student screens,
But what I write does not show up over there.
But what I can do is, I always have the option, and I do this perhaps a little bit too much. There are two ways that you can get information back from the students, or actually here at Columbus State you have three options. I have two options. I went with the cheaper software. I didn't add the monitor on top of it. And so what I can do is I can go in and just say, grab these slides. I want to see what my students are doing. And so I can retrieve, and it will pull up two, and it's working on a third. Oh no, that's what I want. So we retrieved. Okay. So we have the group Dynamite, and we have the group blank, but I know that it's coming from Demo 3, so I know that Demo 3 was here. Students do have the opportunity, on the tablet computers, they can either type or write. They almost always use the pen just because it's right there, it's easier, it's faster. So I have and so actually I can see we've got two stations here. This is the nice tool that you have that I don't. So you can always see exactly what students are doing at any time. So Z was telling me that in his class he just occasionally flashes that up to see what students are looking at on their tablet computer, and if they're, you will have like 15 identical slides, nearly identical, different annotations on it, and then you'll have, solitaire or something. So you can use peer pressure to say, one of these things is definitely not like the other. So you can monitor students like that.
The reason you don't see me is your computer doesn't have monitor.
Yes. I never installed monitor because I never needed it. Another thing that we can do, well, actually, no, let me move to the next slide. So I can give them a conceptual warm-up problem. And one of the things that we can build in here are polls that are basically clicker polls. And so I've got a couple of polling questions. I've got a polling question out there saying, look, tell me about the acceleration of a ball in these 4 situations. The ball is up and is rising. It's thrown down. It's dropped from rest. You just let it go. Or it's thrown up and it's at its maximum height. In which situation is the acceleration the largest? And give them the choices of A, B, C, D, or they're all the same. And so it acts like a clicker. And let's see, got one answer. We can always just guess. In fact, it's kind of nice if we have some different answers here. So just give me some wrong answers as well as right answers. Okay, so. Oh no, you guys are all too good. Okay, so actually this is, and this is when you say, okay, you're perfect. You guys know, you know the physics. Or you can do bar graph. Well, actually, bar graph or pie chart or something like that. You can capture this, and oh boy, and if you're bad like me, it captures in a bad spot. But if you're good, and actually if you're on your own computer, then you can actually move it to a spot where it will stay. One nice thing about the dyno is that students can go back and watch them through an animation where it's stroke by stroke, and you have audio recording on it, so it's paired with the professor's voice, and so they can see all of this at the same time. And the other thing I like about this, I do use clickers in my classroom when I'm lecturing, but here I can ask them to do things like ranking, which is really hard with clickers. You have to figure out, okay, what are all of the possible choices for ranking? And so here, I don't know, Z, do you want to give me, since you've actually got a tablet for this.
I'll do something.
Boy. And so, and actually, why don't you go ahead and submit that, and I'll show them the other way too. I can actually tell students when you're done with this, submit it. And that way, I don't get it until the students are done with it, when they say they've completed. That's also a good way to sort of monitor, okay, are we ready to move on to the next problem? When you've got like 75% of them submitted, you know that it's a good time to stop. And so here I would be saying, okay, got this right, but didn't quite have the idea that I wanted, which was on a test, I would expect to see this as something like A equals B equals C equals D. So I would want you to take those choices, A, B, C, D, and tell me, are they equal, or do we have a greater than or less than? So I can take what's wrong and make it right. And I can pull it up anonymously so that you wouldn't see the name as I did that. Hopefully I would be doing that if I saw a wrong answer. Okay, so let's go back here, and that would be a warm-up kind of question. Let's see. Oh, I might ask. Let's go over here. There we go. I can always ask, and in fact, I try to turn this on at the start of class, and ask, how are you doing? Do you understand what we just talked about? There are students who will definitely never raise their hand and say, I don't understand what we're doing. But if you've got this little request status box going up, you'll notice that that we've got an error message. Okay. That gives them the opportunity to just very quietly within their group say, no idea. Don't know what she's talking about. I didn't catch that at all. And so they can go through and we get, I'm kind of okay with this, but I'm not certain. I don't understand. Or green would be I understand. I also use that for certainty sometimes. So I'll say, Okay, you just submitted a problem. Tell me, how certain are you that this answer was correct? Very certain. Green. Kind of questionable. Yellow. You were just guessing. Red. I want to know whether you think what you did was right.
That's a cool idea.
Okay, so conceptual stuff, and then really the whole reason that I wanted this was because I wanted, so back to the session, I wanted my students to be able to solve problems, and I wanted to see them solve problems. Some of the ways in which I really try to force them to think about problem solving is the first few weeks of class, in the first few Dino sessions, I add this, there we go, add all of these, which is now making it very difficult for you to read. I say, before you do any problem, you have to draw a picture. You have to highlight every single variable. If it's a number, it's probably going to be a variable. And sometimes if it's an important word, like at rest, stop, maximum height, that's also going to be a variable. That's also telling you something. So I want you to identify all of them. And before you start plugging things into an equation, you better tell me what that equation is. So I'm trying to really push them towards all of the tools that they need for problem solving. And then we have to make this, we have the problems. To make it something that was worth their while solving, what I've been doing with my recitations is pulling in test problems from previous years. The only test that I have ever repeated in a class has been the final exam that I've given these classes, and that's just for the last 2 years. Even that took some real angst to decide to do that. Our students don't ever get to see their final exams, and we have a culture at LSUS where students generally don't even ask to come by afterwards and look at them. They don't get their final exams back, so I really shouldn't be freaked out by this, but I had never repeated a test or a final exam until I started this project, where I really wanted to be able to compare problem-solving skills. And so I used paired final exams with a class that I taught a few years ago. So I say this is a test problem. This is the kind of problem that I'm going to be asking you. This is the level I expect you to perform at, and you're going to be having to solve maybe 4 of these kinds of problems on the test. You better be able to do it. Let's work through the process here in a group, and that will give you some practice in terms of getting ready for the test. And so at this point, let's see, is there, and I see I just had somebody submit an answer, so let me go and look at that. All right. Okay, and so now this is perfect. Normally what I do is I turn off the projector while I preview student answers and then pick out the right answer. In this case, I'm just going to say, okay, demo 1, tell us what you did.
Well, I thought this would work, but I'm not sure what to do now.
And so then what we can do is we can turn it to the rest of the class and say, well, let's help them out. Do you think? and we go from there. So we have good conversations about how to solve problems in these recitations. I think if it's okay with you, is there anything else I need to show them here? Yeah, I guess one thing that I haven't shown is that sometimes I guess here and
You wanted to give us privileges so 2 of us can write at the same time, if you wanted to show that.
Insert a blank slide. New panel after, okay. And so draw a physics picture. Okay. And so what I can do is circle control.
Yeah.
And I should have broken it into threes. No.
It should bring up the
It
bell.
should bring up a. Maybe
James.
this is a brand new version of
Yeah,
that.
Jim installed a brand new version that came up a week ago. That was not.
No, it came up this weekend. I saw the email. It came up this weekend. Okay, so we won't do that. One thing, let's see.
It's not working the way the other one does.
Yeah, so we'll skip that. You can actually have them share a panel so that they're
Okay, yeah, it's actually working. It gave us
Okay.
privilege, so.
okay.
It didn't ask you whom to give it though, but it's okay.
Yeah,
So-
usually you can specify
Sean, can you
these
do something
students
on your
together,
screen?
these students
I'm
together.
trying, but it's not showing up.
Yeah, it's not showing up.
Okay, so you can share panels between different groups, so that they might be across the room from each other, but they're still actually working together, which forces them to get to know other people in the room. You can look at what some of the other goodies are here. Chat. I was at a workshop up in Michigan. I had my undergraduate student TA actually in the classroom with my students doing a recitation, and I was monitoring it from up in Michigan. So I had chat enabled, and then I was able to take answers and say, okay, Chris, you need to look at this because I think you're missing a force on your force diagram, your F equals MA problem. And I could sort of drive it from all the way up in Michigan. That was very fun and very cool. You can also just have chat open all the time, either a student to moderator or a student to everybody, so that people can, again, if they're not willing to raise their hand and ask questions, they can ask questions somewhat more anonymously. It's a little bit less worrisome for students to type something in than it is actually raise their hand and interrupt you, especially in a class of 40 or 60 or more than that. And then if you do use it in lecture, and I have been using it in lecture with my upper level classes, you also have a private note area here where they can write over here and take notes about what you're doing at the time, and that will be recorded on their session. They can replay that so that they have some notes in addition to your notes. One thing that I use a lot, and that I've been using more and more, is purple. Not because I like purple, but because purple is sort of the magic color in which I can write on my computer, but I won't be writing on their computers. And that way, I can write things. I'll do this when they're solving a problem, and I'll start to say, well, have you considered using F equals MA? And I hear groans throughout the classroom if it's not purple because I just wrote over their stuff. If I remember to write in purple, then everything that they have there is retained, and I can still, on the screen, write my stuff, and it's not going to be writing over theirs. Okay. I think that gives you a flavor of what Dino can do and does. Let me end this session. Oh, and one thing you can do is force a participant save so that they remember, so they don't have to remember to save it. My students would frequently forget to save their work wherever. And we'll leave.
It's now uploading the voice.
Yeah.
So they can later go back and view the files and annotations and with the voice associated with this specific slide.
And I'm not actually that nice to our students. Actually, it's the computer science or the IT folks. They donated a server to us at LSUS to run Dino on. So we're running Dino on our own campus. We have our own server for it. But they didn't want to donate enough server space that we could run audio with it as well. So my students just have to make do with the annotations and the animation and the slide-by-slide review. But it's still very helpful to them because they can really see, okay, if she did this, And then she went over here and solved for the normal force or whatever, and then came back here to solve the rest of the problem.
You don't have to wait until it's uploaded because we're back to Firefox.
You say that, but I'm not sure. You're right. Okay. Okay. So, here's some examples of student work. I tossed those in just so you could sort of see some completed student work. An F equals MA problem where I can really force them to write out. This was a test problem that I had deconstructed. I had pulled it into all of its little pieces. Draw the free body diagram, write out Newton's second law. Now use your equations to figure out the maximum speed. So I'm kind of, in a test, I don't walk them through it quite that carefully, but here I wanted them to really think about the process of solving that. And other problems. And I guess, so do you feel like you're in an area where you could actually give up a day of class a week? I'm always curious to hear that, especially from people in other fields.
I always feel like I could use about a third more.
Yes, I could use a third more, no problem. I could easily do that. How about some of computer science?
I think it depends on the course. If it's, say, introductory programming, which is very much introducing various programming concepts and then trying them out to solve problems, it could work. I can see. I really think it could. Because we actually have a lab component, which is very much like the recitation that you're talking about.
Yeah. So you could turn computer science, intro computer science, into almost entirely a dynamic class. You really wouldn't need much lecture at all. You could just go back and forth between lecture. Okay, let me have you work on this. Let's talk about while loops and old style programming. Sorry. Let's talk about loops now. You do it. Now let's look at how other groups solve that problem. Very definitely. But other areas?
If you convince us, we might.
Okay, so let me go on to the convincing part. Results. Two different types, two different flavors of physics. College physics, which is our pre-meds, and the bigger class usually, because we've got a lot of pre-meds at LSUS. University physics, which is a calculus-based physics class, tends to be math majors, physics majors, chemistry majors, and some engineering majors. We don't have an engineering school at LSUS, so they have to be pre-engineering. They're planning on transferring someplace else. Classes meet 3 days a week, 50 minutes at a time. And typically we have 30 to 40 students. We have 20 tablet computers. This semester I had 60 students. Budget cutbacks in Louisiana. And still just 20 tablet computers. So I was working with much bigger groups, with more like 3 per group, and in some cases 4 per group this semester. And that's not ideal. It seems like 2 works really well, especially if you then have a couple of groups working together. At first, I was very concerned about the fact that not every student was going to have a tablet. Oh dear. Oh no, not every student is going to have their own computer. It turned out to be really good because it really forced them, especially in the university physics, it forced them to talk to each other. They had to rely on that other person because the other person had the tablet computer because they got there first. And I don't know if you've seen this with, it seems like math and physics majors, maybe engineering majors, to some extent in my classes, have a tendency to just sort of sit there and do this. When you ask them to talk to each other, you ask them to do, talk about a concept or something with your neighbor, and instead what they'll say is, B. Yeah, I got B too. Yeah. I had struggled with getting them to talk to each other for a long time. Brought in tablets, and suddenly they're just talking like mad. Having that excuse, that need to really rely on the other person. And it also meant that a lot of them were getting there early for class because they wanted to be the one writing on the tablet. I wanted to make sure that I did no harm. Sort of like medicine. First do no harm and then try to actually fix the problem. I feel like my classes break down into 3 areas where I want them to be successful. Sort of the 2 balanced areas of conceptual understanding. Do you understand Newton's laws? Do you understand kinematics, to understand how physics works, how the universe works. There are a lot of misconceptions in physics, and so I want to drive them towards a better understanding of how the world works. Problem-solving skills, which is what physics used to be all about. Show me that you can solve these 20 problems on the final exam, and I'll say that you know physics. You might still not understand that when a small car pushes on a large truck, that the force of interaction between the two of them at the bumpers is the same. They might be able to solve the problem perfectly and predict accelerations, but they still don't understand the conceptual underpinnings of it. And then sort of big picture overall course success rate. I felt like that was a little bit imposed on me from above. It was also just sort of, it's something I can measure, and data is always good. So it was something that I could measure and that I was willing to look at. But Louisiana legislature has been getting a lot more micromanagerial in recent years. They don't want to give us money, but they do want to make sure that by goodness, we actually let our students succeed and make sure they all graduate in 5 years and lots of things like that. So it was something that could be measured and would be. And since I'm running low on time, I'm going to skip through this and just go to the summary, because this pulls all those 3 different areas together. Algebra-based physics, the first year, pre-meds. Calculus-based physics, the second year. And force concept inventory, so test of conceptual understanding, pre-test to post-test. I expected this column to actually decrease because I was taking away time from class where we talked about the concepts. I was thinking, at best, this will stay stable. And it's very likely I may have to just give something up in that column. My students aren't going to be getting as much time talking about and understanding and really processing the concepts. So this may take a hit in hopes that the problem solving will go up. And what I saw instead was algebra-based physics went up by 7%. Calc-based physics went up, basically stayed the same, 3%. It did stay the same. Neither of those is a statistically significant increase, but I was thrilled that it was increasing at all because I really honestly did think it would take a hit. So I was happy with that. I didn't do any harm. They tried something new, didn't harm them, that's good. Problem solving. So it's kind of a mixed bag. You can see right here, university physics, they nailed it. They got us, I had a significant increase, 11% increase on a final exam that was paired. It was the same final exam that I'd given previous time I taught the class. My students were better at solving problems. Did not so much nail it with the algebra-based physics class, and that was really a bit of a concern to me. They performed basically at the same level. 2% increase, that's definitely down there in the noise. And that concerned me until I actually got around to looking at this final column of course success, which is how many A's, B's, and C's did we get? So when I looked there, I thought, what's going on here? Same syllabus, same weights to all of the tests, same online homework system, similar homework assignments, same standards for test grading, and exactly the same final exam, exactly the same conceptual exam. And suddenly my students are passing at much higher rates. They're succeeding at much higher rates. And I realized, wait a minute, if this is the case, more of my students are getting through to the end of the semester and performing at the same level as previous years where it was a more elite group, right? I had fewer students in previous years actually getting to the final exam and taking it. So I've got more students succeeding at the same level. I still prefer this, and this is what I want. I want my students to actually perform better. But and here, 10% increase, again, more success with the same syllabus, the same standards, same everything. So more of them are succeeding, and in fact, they're succeeding at a higher level. They're actually performing better. So I was very happy with that. Let me wrap this up. I used a 5-year baseline just because it's very noisy. So these are all of our sections of physics, first semester pre-med physics. The average was around 57%, and this was up at 79%. We kept almost 80% of the students were getting out of there with an A, B, or C, which was just stunning to me. That's not what happens in intro physics classes.
Just the fact that as pre-med, you have filtered your class right there, because people who normally coming out of high school and are looking at pre-med courses are your upper level students anyway.
A lot, yeah. It's usually, and actually that's what I love about physics, is usually we don't get the freshmen. We get the sophomores and the juniors, and they've already, they've been through some filtering as well. But they still, if I go back here, they're still failing in some cases. This semester, fewer than 40% of our students managed to get an A, B, or C. It was a terrible, dreadful year. We took all of these really motivated pre-meds and we crushed their dreams. And we gave them a D or an F, or most likely a lot of them dropped the class and came back and took it another semester. So going from something that's less than 40% up to something that's 80% is just amazing. I broke this down a slightly different way so that you could see where the shift was happening in calculus, space physics. You can see the dark is, the dark is the 4-year average. Excuse me. And so we're getting A's, B's, and C's shifting up towards A's. We actually have fewer B's because the B's tend to become A's in the tablet class. And then we've got about the same number of C's, but that's great because some of those C's moved up. And what we really have is all of these low-performing grades, unsuccessful grades, have been shifted up. So it helps both ways. And kind of my declarations about it. So let me leave you with that and say we can actually get more students through successfully, I think. We can keep more students in the class and have them be more successful while maintaining the same average. Worst case scenario, we're actually increasing their performance. So I'm going to leave it at that and see if you have any questions. Thank you.
Thank you, Cynthia.
So you've described a situation where you have 20 tablet PCs that you must have got through a grant or something?
I got this through a grant from HP, the HP Technology for Teaching grant. So they give you the hardware, and then they give you some money to do with what you please. And I had been hoping to save the money for like student stipends and things like that, but I realized that spending it on Dyna was definitely a very good investment.
Talked a bit about setup and teardown time. You now have a dedicated classroom. You have to share class. Well, I know. So sometimes they do actually exist. But,
yeah, in fact, I have looked around our two areas. We're on two different floors of a building, and thought about, could I just take over that classroom? The problem is most of the grants that I can get in Louisiana, the local Louisiana grants will not fund furniture. And so I need to find a grant that will fund the furniture so I can redo the room. And until I can do that, we roll in the cart and open it up, and students take their tablets out and roll it back to the safe place when we're done.
What is that transition time? I'm just curious.
Oh, it's at the very start of the semester. It seems to take students about 15 minutes at the end of class, which means that I try to stop class at like 20 till if it's supposed to end at 50 till. I try to end class at, say, 10:40 if they're supposed to be out of there by 10:50, figuring that they can donate a little bit of their own time. By the end of the semester, at most 5 minutes on either end. And my students know it's recitation day. They tend to come early just so they can play with the tablet computers and get online and check their email and stuff like that. And then at the end of class, they're very good about just wrapping it up, uploading stuff. I have them share stuff on our course management system, Moodle, so that even though only one of them is on Moodle, all of them have access to that shared Dino notebook. So they upload things to our course management system, and then all of them have access to it. It's 5 minutes.
The other question is kind of associated with that. Have you noticed maintenance issues? I mean, have you wear and tear? Just
on the tablet computers.
Yeah, tablets. Just
Those are remarkably solid little things. They've been working well for us. This is the 3rd year of use in them. I think my biggest complaint about them was there's a really flaky mouse on the side in that particular year. But once I found the fix for it, which is just when it starts acting crazy, you just rotate your screen 4 times and it's back to acting normal again. And that was such an improvement over the first solution that we had to it, which was nothing is working. I have to reboot. That was a problem. When you had to reboot, that was not acceptable. But when you realized, okay, rotate, we're good.
Makes sense.
So you didn't, I don't think you explicitly said it, but you seem to have implied that you were able to give up 1/3 of your time and still cover your topics that you...
I do still cover my topics. It has always been a struggle for me to get to fluid mechanics, fluid dynamics, mechanics, and first semester physics. So even before this project, sometimes I did and sometimes I didn't. Now I pretty much don't. So I just don't get there. I gave up that. I tell my pre-meds especially, this is something you want to look at. It will be on the MCAT. You're not going to see it anywhere else. But sorry.
Georgia actually does not require it covered.
Yeah.
The fluid mechanics is
What about your assessment? Your final assessment at the end. I mean, is that
like
set up?
So like course assessment, students assessing me. It's a little bit hard to say. This year we haven't had any because we transitioned from the SIR2, which is ETS administered, nationally normed assessment of teachers by students. That was very expensive. We moved from that to the online one and got very few responses, and it also was not nationally normed, which they told us it would be. So this year is going to be a complete loss. My overall evaluations didn't really significantly go up or down. That's actually one thing that I haven't looked at, and I need to add that data to this. I've written it up as a short paper for a workshop, but I haven't written it up for this data up for a journal yet, and I need to go through and look at that. The biggest frustration that my students seem to have with this was the first year when technology was much more of an issue. These days they just sort of accept it as, oh yeah, that's what we do in physics class. We go in, we work on tablet computers, and they do say that the recitations are more valuable than the textbook, more valuable than online homework, more valuable than my lectures, and let's see. The only thing I'm thinking about what I asked them on a survey that I gave them this year. They still have that deep-seated belief that mimicry will do it for them. So I was doing some screencasts for them, walking them through some problems, uploading that screencast for them so that they could watch, basically hear me solve a problem and watch my tablet solution to it. And they really liked that. That was the only thing that they liked better than the recitations, because I think they could repeat it and repeat it and repeat it. They could basically do the rewind. Wait, why did she do that? Rewind again. So they seem to think that it works for them.
Did the students still come to your office for individual?
Oh yes, yes they do.
This.
They definitely do. It does seem like it has given them a nucleus of a study group though. So it has taken some of those students. I think some of the ones who would not have succeeded, part of why they wouldn't have succeeded would have been because they would have been struggling by themselves. And now they have immediately at least 1 or 2 other people that they can turn to, who they know, who they have worked with, and who they can study with. So it forces them into a study group almost. And that's one of the reasons why I keep them in one single group throughout the semester.
do you consider different factors in putting the groups together, or is it random assignment?
It is strictly geographical. So basically, look around you. You need one computer for every 2 or 3 people. So, and actually, it's basically geographical. I have tried doing some of the other more careful grouping of students, and in the end, it just is so much easier to manage if you just say, okay, find people who are close to you.
Yeah. You technically could assign random groups of whatever size that you prefer, but
especially with this cross.
Yeah, there is a way to set up. If you had one tablet per person, you could you could set up random groups anytime you wanted, because you can just tell Dino, give me groups of 3 randomly, or give me groups of 5 randomly, or give me groups of 2 randomly, and just
that would be
work them together.
If they didn't even know who
the
person was at the other end.
There are lots
can't
of.
do that if you find it appropriate.
Did it take you long to learn how to use Dino?
There are still a few times when you can see that the things that I don't use where I think I know where that ought to be, but where is it? Like the shared control aspect of it. Most of it is pretty straightforward, though. It's and you can go through, and even if you're just doing things like pulling up their panels and showing them to the class, or even if you're just doing that, that's such a powerful thing. That all by itself, to me, that sold me on Dino, because I could very easily pull in the good work, and then I could layer on top of that in later semesters things like adding the polling. Actually, the polling is really easy, because you just pull in. You've got a PowerPoint, and there's a Dino plugin that says I want to add a poll right now.
Is there any cost associated with Dino for students?
No, not at all. It's free for students. In fact, this semester I'm teaching a first semester university physics, and I knew it was going to be a small section, and I knew that the faculty member who was teaching after me would not be using clickers. So I wasn't quite willing to make my students go out and buy clickers for 4 weeks of a first semester physics class. So what I've decided is it's a small enough class. We're going to be using Dino throughout, and that way they have basically free clickers, because they've got the free polling capability, plus they've got everything else on top of it as well.
So you have to have some kind of base that you have set up to operate software, and
that's my base right there.
that's it.
Yeah, that's it. It's just a tablet computer. It's all. So my tablet is identical to the student tablets. And I'm just running Dino on it. You do need wireless networking, and preferably a nice stable wireless network. But I haven't really had technical issues at all with this.
You might have noticed at one point I was out and it was showing error, but after two retry clicks, it caught up. In the background is working. If the network drops or it loses the signal, whatever, it will work in the background and try to fix itself. And it did, without me doing anything, but hitting that retry.
How many other departments or faculty now that you're into it? I mean, has it sort of filtered out?
I should admit, I'm a Department of Chemistry and Physics. I'm in a Department of Chemistry and Physics. We've had some chemists using it. Biology, the genetics professor uses it. It's very useful for some of the planet table sort of stuff. And another biology professor uses it for their basically critical thinking in biology class. But it hasn't spread beyond that, in part because those are the 3 departments in my building. And, it's a big, awkward cart that steers like a whale. And and so it's going to pretty much stay in the building. And so physics, biology, chemistry, we're the ones who use it.
I was just curious because as it filtered out to other departments, how it would filter through to the administration, beginning looking long range as far as technical expenses and
And actually, the way that we implemented it, it's pretty cheap. We bought the 21 licenses that we have, and we host the server ourselves, as opposed to the premium way to do this. If you want to make it as expensive as possible, is you say to Dino, let me use your stuff, let me use your server, let me use your everything is over on Dino, and they take care of all of the technical updates. They do everything for you. And it must be lovely, but it's very expensive as well. So we host a Dino server. They had an extra server. IT somehow always seems like they have an extra computer sort of sitting around not being utilized. So they had an extra server. They gave us server space. And usually about once a year, once every 6 months, they will donate a half day or a couple of half days to updating us to the very latest version of Dino. That costs, I know that it's less than $500, maybe $300 for the 21 licenses that I have, just to keep us being able to keep the updates, so that we can go with each new version. And Dino really has been getting better and better. I like the new versions much better than the old one. It was a little bit clunky in the beginning. It's getting much smoother. So that's something that in ordinary years I can fund out of my department budget. They did actually freeze my general fund budget at the end of March this year, so I've been running on absolutely zero for the last couple months, which means that I'm a little bit worried. On the other hand, I have to pay for it in August, so by then I should have next fiscal year funds, and I'm hoping that I can just sort of pay for it and forget about the fact that they're probably going to come back and freeze my general fund budget again in March.
Is there a license, user license, I mean, as far as the numbers, or once you got a license, for your use?
So I have the 21 licenses, and that's how many basically students we can have in a live session at once. But once we've paid for that, students have a free download. The Dino Reader, the Dino download is actually free for students. And so if they save their Dino session, at any time they can go in on their own computer or on the LSUS computers that have Dino on them and replay Dino. So all of that part is free for students. It's completely free for students, and it's a couple $100 a year for the department.
Thank you all very much.
Thank you for
Cynthia,
sticking with
very
me
much.
for so long.
Thank you both for coming. Thanks for Sean.